Okay, today's talk is by Professor Gunnar Hornig from Dundee, Scotland, and we are very happy to hear his talk on magnetohydrodynamic relaxation, helicity, and minimum energy states in magnetized plasmas. Gunnar, to you.
So thank you very much, Renzo. Thank you for the invitation, also to Jose. The topic which I've chosen for today's talk is very much motivated by the theme of the seminar series, so geometry and topology. As we will see, the main quantity I'm talking about today, helicity, is a topological quantity, and the energy is a geometrical quantity, and the talk is all about the relation between the two. Because I expect that maybe not everybody in the audience is familiar with magnetohydrodynamics, I will give a little bit of an introduction into that, and the experts might excuse that they've seen some of these things before I come to the main results. Right. So magnetohydrodynamics is a theory which combines the Navier-Stokes equations and Maxwell's equations to describe the evolution of a plasma, so electrically conducting ionized gas. And the main equation which we are interested in is the induction equation, which is derived from Faraday's law. And that induction equation has on the right-hand side two terms. The first one, the curl of V cross B, describes the effect of the flow of the plasma onto the magnetic field. And there exists a corresponding term in the momentum equation, which describes the action of the magnetic field on the flow via the J cross B force. These two terms give you an exchange of magnetic and kinetic energy, and then there is also a dissipation of magnetic energy, which is the eta Laplace B term, and a corresponding viscous term in the momentum equation, which leads to a dissipation of kinetic energy. These terms then show up in the energy equation as well as terms which heat the plasma. So we have an exchange of magnetic and kinetic energy and a dissipation of both magnetic and kinetic energy due to these dissipative terms. Now, these dissipative terms are usually quite small. In particular, for astrophysical plasmas, we can have Reynolds numbers which are rather large, and the Reynolds number describes the ratio between these two terms in the induction equation. So the curl V cross B term is typically much bigger than the eta Laplace. So if you want to draw a diagram, you could do this in this way. You have three forms of energy: magnetic, kinetic, and internal. There is the option of an exchange between magnetic and kinetic energy via ideal motion, so even in the absence of any dissipation. And then there is the dissipation of magnetic energy, which heats the plasma, and the dissipation of kinetic energy, which heats the plasma. Eventually, the plasma can radiate and can get rid of its internal energy, either by radiation or by heat conduction with the environment. What is not included in MHD, at least not explicitly, is a further loss energy loss mechanism by accelerating particles in electric fields, but that is not directly accounted for in MHD. Right. So I mentioned the ideal exchange of energy between the magnetic and velocity field, and this ideal plasma dynamics implies a conservation of magnetic flux, and this is called Halphane's theorem. Or if you write it in differential forms, you can see that this is the Lie derivative theorem for the magnetic field. So this means that the magnetic field at some later time t, so see here, is related to the magnetic field at an earlier time via a mapping F. So this F star here means the pullback, and you can think of B as a two-form if you want. And the F is the flow of the velocity field, so d by dt of F is our velocity field of the plasma. And that velocity field then generates this isotopy F, which essentially deforms any magnetic field in your domain. And I try to illustrate this down here with just a simple flux ring, so a tube of magnetic field lines, and they get deformed or can be deformed under this mapping. But for a given cross-section, the black disk here, the magnetic field integrated over that cross-section always remains the same. Right. Now the main subject of this talk is magnetic helicity, and this is defined as an integral over the vector potential times the magnetic field. And this integral is gauge invariant, that is, it doesn't depend on the vector choice of the vector potential. If we choose a volume such that the magnetic field is tangent to the boundary everywhere. If we, so we can derive directly from Maxwell's equation an evolution equation for the magnetic helicity density, so A dot B, and that equation has the divergence of helicity current in it and a source term on the right hand side minus 2 times E dot B. If you integrate this equation over a domain such that the helicity current vanishes on the boundary, then you end up with this equation here, where the change of the total helicity is due only to this source term, minus 2 times integral E dot B. The helicity integral is a measure of the linkage of magnetic flux in the domain. And it's great to have Keith Moffat here in the audience, who actually coined the notion of magnetic helicity and gave its first interpretation. And I try to do this here with this simple pair of flux rings. So you think of these two rings as bundles of magnetic field lines. They have an orientation, and depending on the relative orientation between the two flux tubes, you can have either positive or negative magnetic helicity in this configuration. more generally, you can interpret the helicity as the helicity is a topological invariant. So under the ideal deformation, which we discussed before, the electric field is perpendicular to the magnetic field. So the the term on the right-hand side of this equation here vanishes, and that means the helicity doesn't change under ideal deformation. Another way of seeing the same thing is to write the helicity as differential form, as an integral over differential form. So here omega A is the one form associated with the vector potential. So you plug the vector potential, the vector, into the metric, and then you get a one form. And d omega A is the equivalent of the magnetic field. It's a two form. And omega A wedge d omega A is exactly the integrand A dot B. But the way in which this is written means that this is a coordinate-free representation, and from that one can immediately deduce that the helicity is invariant under arbitrary deformation. I explicitly wrote this down here, but that is just another way of stating the same thing. Right, if helicity were always conserved and everything would be always ideal, there wouldn't be much going on in our plasma. But fortunately or unfortunately, depending on the point of view, we also have processes like magnetic reconnection. And I give a little cartoon here to show how the topology can change under magnetic reconnection. So we have two flux tubes here, a blue and a red one. They get into close contact, which means there is a strong current between them. And that current dissipates, and in this process generates an electric field first, localized electric field, and then following from that also a localized magnetic field, which is superimposed to this field of the two flux tubes and changes the connection. I showed here in the second row also the view from above, where you see how two almost opposite directed magnetic flux tubes change their connectivity. This scenario is slightly different but similar to the surgery which is considered in knot theory. So if the flux tubes were exactly antiparallel and lie in a plane, it would be actually the same as the surgery. But since we have in typically three-dimensional configurations, the process is slightly different, and it actually adds a small twist to the connected flux tube. And that is consistent with our equation for the helicity evolution. Remember, that was d by dt of the integral of a dot b equal minus 2 times e dot b. In that the electric field which is necessary for that process is very localized in the domain. So we integrate over a rather small volume where this quantity E dot B is non-zero, while in most of the domain it is close to zero. And that means that this source term is much smaller than the typical value of the integral a dot b, normalized to a typical timescale, so a dynamic timescale. Tau dynamic here symbolizes a dynamic timescale. So that is typically something like an Alfvén crossing time, so the time the perturbation needs to travel across the domain under consideration. So that means that even for this reconnection process, the helicity source term, the integral e dot b, is rather small. One has to be always a bit careful with all these statements, because the helicity can be also zero, and then of course nothing is small compared to zero, but one has to interpret the right-hand side as a kind of typical quantity here. Right. So these kinds of processes, reconnection and ideal exchange of energy between magnetic and velocity field, take place in plasma relaxation. So if we have a high energy plasma with a magnetic field and we let it relax, then what it tries to do is tries to minimize the energy. However, as I've shown in both the ideal and also in the reconnection process, the helicity is conserved. So we roughly maintain the magnetic helicity, but the energy decreases. And what happens in a high magnetic Reynolds number plasma is that the motion quickly becomes turbulent. So we have all kinds of scales in the plasma. We have many reconnection events, larger ones initially, and then lots of smaller ones, until the magnetic field has exhausted all its energy and settles down to a lower energy state. And in that energy state then only dissipates on the rather large time scale given by the enormous magnetic Reynolds numbers we have. So this cartoon down here is just a cartoon and describes a typical situation of a turbulent relaxation of a magnetic plasma. This number 5 here is more or less arbitrary, but indicates that the turbulence usually doesn't take much time to dissipate the energy, and something like 5, I think, crossing times is quite typical for most of the energy to be dissipated. Right. This kind of scenario was behind an important application where already in the 70s, J.B. Taylor predicted that the reversed field pinch will settle down after an initial turbulent state to a linear force-free field. So curl B is lambda B, preserving the total helicity in the domain, so in this toroidal vessel, and the toroidal flux. And this prediction was verified and was very successful. The linear force-free field is one which minimizes the energy, and we'll see a little bit more how that comes about in the next slides. So before I do this, I want to introduce Arnold's inequality. So this is our kind of main subject today. Arnold published this in 1974, initially in a Russian journal, and then later it got translated. And the inequality is applied to a simply connected and compact domain with a magnetic field, which is divergence-free and tangent to the boundary. And it says that the magnetic helicity, or more precisely the modulus of the magnetic helicity, is less or equal to over c times the integral over b squared, or b squared half the magnetic energy. So first of all, if you compare this with Arnold's original publication, I introduced here the factor 1/2 to make it more look like the magnetic energy, which physicists are familiar with. And then that also leads to the factor 2 here in front, which is slightly different from what Arnold originally wrote. But then also we have this constant c, and the important part here is that c is a constant which only depends on the geometry of the domain, so not on the magnetic field itself. Anyway. If I want to illustrate what this inequality tells us, if we take again a simple flux ring, and we start off with an untwisted flux ring, then the helicity of that ring is 0, so the left-hand side of the inequality is 0. And that in principle allows that the right-hand side could also be 0. And indeed, if you try to reduce the energy of this flux ring, you could do that by shrinking the radius of that ring. You have to preserve the flux, so the flux has to go somewhere, and indeed you can stretch it out in the vertical direction, or z-axis if you want, and make a very tall but very narrow flux tube. And you can shrink the radius arbitrarily far or arbitrarily close to 0, and thereby get with your energy arbitrarily close to 0. So indeed, for helicity being 0, you can dissipate the magnetic energy as far as you want. The same situation for a pair of linked flux tube does not, or the same scenario does not work anymore, in that if you have a pair of linked flux tubes, then of course at some point shrinking one of these flux tubes, you will encounter the other flux tube, and that is an obstacle. And the best you can achieve here is that one flux tube wraps around the other one in a symmetric way, and I left this flux tube open here a little bit to show that it links the other one inside. So this is kind of a quick illustration of what this inequality means. But if we, for a moment, think about this a bit more, then it's actually surprising that we don't have more of these inequalities, because the argument which I just gave, that the topology is here an obstacle to reducing the energy, of course would work as well for any kind of higher order linkage or knottedness of magnetic flux. So you would expect that one can write down similar inequalities with the left-hand side, which describes maybe other forms of linkage or knottedness. Unfortunately, we don't have any nice integrals, similar to the helicity to describe these other forms of knottedness. The closest we get to this is maybe described in a paper by Friedman and he, who used asymptotic crossing number to describe disjoint flux tubes, or the topology of disjoint flux tubes in a domain. But this is also still a very artificial situation from a physical point of view, and that is not easily applied to plasmas or to realistic plasma situation. Right, so minimum energy states, what kind of states minimize the energy under given helicity? One can show, using a very simple variational principle, that the fields with minimum energy for given helicity are linear force-free fields, so eigenfields of the curl operator. And if the reverse statement does not hold, so not every linear force-free field is a minimum energy state, and for instance, you can have things like kink instability or linear force-free fields with high values, lambda. If we have such a field, a linear force-free field, we can find a vector potential, A, just as 1 over lambda times B, and we can, of course, always add a gradient of a function which wouldn't change the curl of this vector potential. If we plug this into our helicity integral on the left-hand side, then we end up with 1 over lambda, or 1 over the modulus of lambda, times the integral b squared. And that means that the inequality is satisfied if we choose for C the smallest possible lambda which we can find, right? Smallest possible lambda means largest possible value of 2 over lambda, and therefore that satisfies then this inequality for all force-free fields. So that's why C can be chosen as the minimum eigenvalue lambda of our linear force-free field, the minimum eigenvalue of the curl operator in the domain. And indeed, for the initial scenario for which Arnold wrote down this inequality, we have a compact domain, and B is tangential to the boundary, and then the spectrum of the curl operator is discrete, and there is indeed a minimum eigenvalue, where minimum eigenvalue means minimum modulus of the eigenvalue. Right, I was told to stop somewhere halfway through and ask for questions. So please, if you have any questions so far, let me know. Check the chat. Seems to be fine. So if there are no questions, then I carry on. So which minimum eigenvalues do we obtain here? First of all, we can rewrite our inequality by just dividing the inequality by the energy. So then we get a ratio here on the left-hand side, helicity over energy is less or equal to over the minimum eigenvalue. And this minimum eigenvalue can be calculated for some simple configurations. For instance, for a sphere of radius r, we get that the minimum eigenvalue is 4.49 over r. And for a cube, we get pi times square root 3 over L as the minimum eigenvalue. So these eigenvalues scale with the, or inversely scale with the size of the domain, but are quite similar for simple domains. I have here also an example where Jason Cantarella calculated the linear force-free fields in a spherical shell, so between an inner radius A and an outer radius B. The outer radius is roughly 1, and the inner radius is increased from 0 to about 70%, or 0.69 of the outer radius. And you can see how the eigenvalues, the minimum, the lowest eigenvalue, increases as you squeeze the magnetic field into a thinner and thinner spherical shell. So more distorted domains require more energy for the same helicity. That's another way of stating the same thing. Right. If you have an inequality, you can always read it in two ways. You can either read the left-hand side as fixed, and then you minimize the right-hand side to get to the lowest possible value, or the right-hand side is fixed, and you minimize the left-hand side. So we can either think of these fields as fields which minimize the energy for a given magnetic helicity, or we can think of it as maximizing the helicity for a given energy. And in order to do this, to keep the symmetry, you can, instead of looking at h of b and the E of b, the energy, separately, you can divide and multiply with c, our constant, the minimum eigenvalue, divided by 2, to obtain a dimensionless quantity, which now varies between -1 and 1. And this dimensionless quantity can help you to interpret what kind of situation you have in a plasma. If the quantity is close to 0, then you are far away from these minimum energy states or maximum helicity states. And if it's close to 1 or -1, you're close to these maximum helicity or minimum energy states. And that is a good way to give meaning to statements like the helicity has changed by that much, which is often difficult to interpret because you don't know exactly whether the quantity is big or small. Only if you compare it with one of these extreme states, you can say something more concrete about whether that is a small change or a big change. Now, the energy, the inequality requires a simple connected, compact, and magnetically closed domain. And this is typically way too restrictive for most applications. Instead, what we need are results for things like a torus or even open boundary conditions. And that is what I want to try next. So in order to find whether we can generalize this inequality for more typical domains, I go back and look how we derived the inequality in the first place. So this is a combination of applying first the Cauchy-Schwarz inequality and then subsequently the Poincaré inequality. And if you look up typical papers, and Yoshida and Gi, 1990 is a good reference, then you find that this Poincaré inequality requires, if you don't have a simply connected domain, that A and B, the two vector fields involved, are part of the space L2 sigma, and that is the square integrable vector fields which are divergence-free, tangent to the boundary, and also satisfy a zero flux condition. That is, if you integrate over a cross-section, arbitrary cross-section, sigma of your domain, then the total flux vanishes. This condition is not a big restriction if you have a simply connected domain, as every cross-section across a simply connected domain would satisfy this. But it is a restriction if you have something like a torus, solid torus. Right. This is, first of all, quite a severe constraint for both A and B, but it can be actually relaxed because we've seen that our vector or helicity integral is gauge invariant, so we can add an arbitrary gradient to the vector potential. And that means that for A, actually, we don't need the divergence equals 0 and tangent to the boundary condition. So A could be just a square integral vector field, but B still would have to satisfy these conditions if we have a non-simply connected domain. But so this is a first result. We can indeed look at this inequality also in a torus, but then we have to make sure that B satisfies this is part of this set L2 sigma.
Gunnar?
Right. How would, yeah?
Please go back to that slide just to make sure that I understand. So in this set, there you have a U, and U is just a representative of either A or B.
A or B. Mm-hmm.
Very good. Thank you.
Okay. Right. So how does that look like in reality? So instead of a torus, we use a cylinder with periodic boundary conditions. So this makes just the geometry much nicer. And then we are looking for the minimum energy states, which we know are linear force-free field. The lowest linear force-free fields with the lowest eigenvalues are symmetric linear force-free fields, and we know these solutions. These are the so-called Lundquist solutions. That is a combination of Bessel functions for the phi and z direction of that component of the magnetic field. If we use this form for our magnetic field and evaluate this condition that the flux across a given cross-section sigma has to vanish, then we end up with the condition that the first zero of the Bessel function has to vanish on the boundary. Sorry, that the first Bessel function of lambda times r, where capital R is the boundary value, has to vanish. So lambda times r has to be the first zero of the first order Bessel function. Now, this is quite a restriction, and I try to explain this here on the next slide. So we have our periodic cylinder here. Sigma is a cross-section of the cylinder. If we think of this periodic cylinder as a torus, then sigma is a cross-section of the torus. The condition that the flux through this torus vanishes is quite restrictive, and we would like to get rid of that. What the physical meaning of this condition is that the helicity of the in the torus is actually independent of any flux through the whole of the torus if the total flux through sigma vanishes. An alternative condition for the same property is that the flux through sigma does not vanish, but the line integral over the dotted red line here, so a line on the boundary of this torus, vanishes. Line integral over the vector potential. That condition ensures that there is no flux going through the whole of the torus. So either one uses the condition that there is no flux through the whole of the torus, or that the flux in the torus vanishes, both lead to the helicity being independent of or being well defined. Right. So if we don't want the condition that integral over sigma is 0, then we have to use this other condition, integral a dl equals 0. But that means that we don't have a discrete spectrum anymore for our eigenvalues. So we end up with a continuous spectrum for our eigenvalue. Right. So here I wrote down the actual solution for our Lundquist fields. You can find here the term which ensures that the integral a dl is vanishing. So I subtract the value of the vector potential on the boundary, so that vanishes eventually, and integral a dl is 0. If you now plot the ratio of helicity over energy for these kind of fields, then you find a curve like the one I showed here in blue. So on the horizontal axis is lambda, and the vertical axis is h over e. And surprisingly, you find that, first of all, it starts at 0 and not at infinity, which we could easily expect since lambda shows up here in the denominator in various locations. And second, there is a well-defined maximum, even though we don't have a discrete spectrum. There's a maximum h over e. And that maximum occurs at j naught equals 0. So the first 0 of the zero order Bessel function. While the previous one occurred at j1 equals 0. So to summarize this, if B is divergence-free and tangent to the boundary, and we now drop the simply connected condition, then we can still apply our inequality However, we have to make sure that we are in one of these two options. So either our magnetic field vanishes over the, either the integral of the magnetic field over cross-section vanishes, then the minimum eigenvalue is 3.8 something, the first zero of the first order Bessel function, and or the second option, our integral over A dl is 0 on the boundary, and then B only needs to be in L2 lowercase sigma, that is, it only needs to be divergence free and tangent to the boundary, and we get a lower lambda min for that. Right. One can do the same for an open domain. So for an open domain, that means flux, that our cylinder is now not periodic anymore, and at the top boundary and the bottom boundary, a field can enter and leave the domain. If one usually wants to calculate the helicity of such a domain, you would use the relative helicity, that is, you would find a corresponding potential field, or in general reference field, which satisfies the same boundary conditions, and calculate A plus A P minus B times B minus BP as a relative helicity integral. In our case, we can take for this reference field just the Z component, or the Z part of our magnetic field, and surprisingly we end up with exactly the same result as we calculated previously for the periodic case, with A tilde given here, so the vector potential which we obtained by applying the integral A dl equals 0 condition. So again, we end up with the same curve which I've shown here, and the same maximum. Finally, I want to generalize this even further, and instead of considering just the modulus of the integral of A dot B, to consider the integral of the modulus of A dot B, which is typically much larger than the modulus sign outside the integral, because in a typical plasma you have regions both of positive and negative integrand A dot B. So that would give us in general or more useful inequality. And indeed, we can show that applying the Cauchy-Schwarz inequality twice, and then applying Poincaré inequality as before, we end up with an inequality where the absolute sign are now under the integral. However, there's a price to pay for that. And the price to pay is that this integral is not gauge invariant anymore, and correspondingly we can't easily relax the conditions on our vector fields. So far our two vector fields, A sigma and B sigma, have to stay in this rather restrictive set L2 sigma, which requires this integral of B over any cross-section sigma to vanish. So this is still a little bit unsatisfying, but we're working on trying to get more useful versions of that inequality to work. Right, so that leads me to my summary. I hope I've shown you that the helicity over the energy is a good quantity to describe and compare evolution of magnetic fields in plasma, and in particular in the relaxation, turbulent relaxation of a high Reynolds number plasma, we tend to maximize this ratio, and that we can extend Arnold's inequality, which gives us a relation between the energy and the helicity, to multiple connected domains as well as open domains using relative helicity, provided we make sure that our fields are in the appropriate set, and states with maximum helicity per energy, first of all, do exist, and at least I've shown this for the periodic cylinder, and corresponding upper bounds for the ratio of helicity over energy can be found. There's a lot to do still in trying to formulate these things in a way which as applicable as possible to real situations. But for the moment, that is all what I can present here, and I want to thank you for your attention.
Okay, thank you very much, Gunnar. I think we have surely some questions. I see a hand from somebody. If I may, I ask you something, and then I invite people to come up with questions. Gunnar, you showed at a certain point option 2 in your minimum energy state slides, and that was considering the integral of ADL equal to 0. Yes.
Is that the slide? Yeah.
Yes. Now, when so my question is, comes to mind a work, a JFM paper, I think was 2 or 3 years ago, by McTaggart and Valley on helicity, gauge invariance of helicity in multiply connected domains. And if I remember correctly, the correction, say, to helicity in order to have it gauge invariant was to involve ADL integral different from 0 as one of the, say, strength contribution in the correction. But in this case, if this is 0, that means we have problems in interpreting the gauge invariance in that context. With can you comment on that, please?
Yeah. So maybe one can make this slightly more general. So I've chosen 0 in order to describe a situation where there's no flux outside linking that particular domain.
Yes.
If you have a situation like in a tokamak where you have flux linking the domain and you know that flux, then you can, of course, also write on the right-hand side of this equation the exact flux which you want to describe here. And then you are aware that what you measure is the helicity in your domain with the linking of the outside flux. So this, it can be something different from 0, but then you have to give it the right interpretation. Right? It's not just the helicity of that particular domain, but the helicity of a configuration of that domain plus some outside flux.
Thank you. Clear. Thank you. So welcome questions from the participants. Keith, I see your mic is open. Hello.
Yes, hello Renzo, and hello Gunnar.
Hi,
Nice
Keith. Great
lecture.
to see you. Yeah.
Very nice lecture. I enjoyed that. Some nice ideas,
Mm.
especially regarding these eigenfunctions in the cylinder. Just one point I wanted to make. When you talk about the relaxation of energy at constant helicity, there is energy in the fluid. The magnetic field, the Lorentz force, generates a flow. And if the fluid is viscous, then energy is dissipated by viscosity. Whereas magnetic field is only dissipated directly, or helicity is only dissipated, you might say, if the magnetic diffusivity is non-zero. So if you have a non-zero viscosity, but zero magnetic diffusivity, then you have an exact situation. Energy decreases and helicity is constant. And that is, of course, what happens when a magnetic flux tube in the form of a knot relaxes initially to a minimum energy configuration. But when it does so, you tend to get current sheets, and then of course you can't avoid magnetic diffusive dissipation coming in.
That is great. Yeah. So in turbulent plasmas, often the kind of viscous dissipation is actually more efficient than the resistive one. And so what you often see is that the turbulence distributes magnetic energy to kinetic energy, and then that is dissipated by viscous heating, and that is the kind of big energy loss channel. And then there is a smaller energy loss channel via direct resistive heating. But depending on how large your magnetic Reynolds number is, this resistive heating can be rather small. And then very strong currents are generated.
Yeah.
I agree, yeah.
Okay, more questions? Okay, well, if none, thank you again, Gunnar. Wonderful talk. Thank you so much.
Thank you.